Testing, 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 testing. Ken, let me know if you can hear me. This is a secret message just for you. Thank you. Hello, good evening to you. You're very welcome here this evening. I'm sorry about the rain. That might be all we're going to be able to hear the whole evening. Hope it's not too intrusive. I don't have a rain filter to put around myself. We just have to deal with it. Hopefully it won't leak onto anything important. Is the plan. So, good evening. Hello, I'm Robin and this is Molten Modular DIY. This is part 5, I believe, in a far more parted series of videos on building the MKI XES EDU Erica Synths educational range of DIY modules. We've got pretty far. Look at this. It's really starting to look nice now. We have the VCO that we started with, then the dual VCA, then we built the case and the power supply, then we did the envelopes. Now I built the second envelope this afternoon when I suddenly realised, oh heck, I haven't built the second envelope, because we did the first one in the live stream and I said I would build the next one before we did the next module, and here we are. So I had to get that done, tested it out, seems to work fine. They're good, simple envelopes, like that a lot. I know, Simon, you only check Instagram once every 3 weeks. So I appreciate that. I will. I'll go and check that. Don't worry. So yeah. So now we're on to the sequencer, which I have here. Now, having a little browse through the online documentation, this looks like a bit of a heavy thing. It's going to involve two breadboards, so that's quite exciting. And I already know that my breadboards are upside down and back to front. Are they both the same? Is another question. Yep, seem to be. But I'm not going to be disturbed. Oh look, looks like they have things that make them slot together. That's remarkable. Does that actually work? Look at that. Cool, blow me down. Fantastic. Well, we'll look at that in a minute, obviously. So I'm not going to try not to talk for too long. I just need to get into it because I think this is going to be a long one. And, you know, we're all supposed to be watching Star Wars movies. Whereas instead what we are is watching me struggle my way through another fantastic build. So the purpose of this evening is to breadboard sequencer, try to get it working, try to see whether we can understand what makes a sequencer tick, what puts the sequencer together, and how that works. And we're going to build it together and try to grasp the component nature of these things. It's very exciting. And then tomorrow, all being well, we'll solder the thing together and test it. So there's the front panel. It's a 5-step sequencer, which I love the fact that it's a 5-step sequencer, although you can also dial it down to 4 or 3, as I understand it. But 5 steps, oh, that's just the greatest. Yeah, that's a load of soldering on there, that is. Lots more of these vertical resistors by the looks of things. So cool, but we're not really going to be looking at this bit until tomorrow, so I'll put that to one side for now. What we will need is the components, and because these now come with a bill of materials, it'd be really good just to go through that to give us an idea of what we've got, so we're not trying to worry about it or think about it or overthink it or any of those sorts of things. So if you're ready, I think we should probably begin. What button am I pressing? Oh dear, I'm so smooth. Oh, I am totally on fire today for this. Doesn't matter. Let's just do it. Let's find a button. Let's say this one and go with it. Look at that. There we go. So, well, you don't want that. we want the other one. That's it. The one that we get to see the manual for a bit for. Okay, see that first. So this is the sequencer. This is the introduction. So if you've not been to one of these before, just to explain that what I do is I read through the documentation. This is the process of me looking at the manual, trying to understand it and trying to discuss that with you as we go along and then build it together. That's the plan. I haven't come here with special knowledge or an understanding, or I haven't built one before. I'm here to learn. And so this is going to be slow and long and methodical, and probably with the odd tricky bit. But that's what the plan is. That's what we're here to do. So that is what we will endeavour to achieve. So here you can get the manual from the Erica Synths website, from the shop. Go for the sequencer. You'll find the manual there, and that's exactly what we're using here. So if you're new to synthesizer building, might have run into this issue. You just set up your first VCO on a breadboard, spent a good long time troubleshooting, and then you realise you have nothing to actually control it with. Don't worry, here's a simple 5-step sequencer. Excellent, thank you, Moritz. That's awesome. So there is the circuit diagram. That's the word I'm looking for. Circuit diagram. So there's going to be 5 of everything, isn't there? So you've got 5 things here along the top. You can't see that with my finger. I'll do it with the mouse. 5 things here. 5 things there, like with diodes on. Oh, they've all got diodes on. Those are diodes going backwards. So that's a feedback thing. I'm not going to try to guess at it. And then there's 5 things here. So look, switches that go in. To stuff, to a gate, to a clock. A reset. Interesting. And there's also a chip with some pinouts on. Okay. Interesting. So let's have a look through our bill of materials just to make sure we have everything right. So this might involve some measuring of resistors. But I might, because that takes a long time. Well, no, I am going to need to do it because we're building the thing, aren't we? So I'm going to have to do it. Oh, I suddenly thought there we could leave that till tomorrow. No. Right. Keep focused, you fool. Keep focused. So let's swap to this overhead one so that you can see what's going on. Yeah, no, I don't ever use the resets. No, I understand that. So we've got some diodes. They're fine. We know what they are. But let's try to get down to our resistors first. So there should be a pack of 14 of one type. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So those are very much likely to be the 100Ks. So I'm just going to go with that being 100K. I'm not even going to measure it because I'm that cavalier at this point. Because everything else more or less is ones. Except for this lot here, which is a big bunch of them. 7. Oh, okay, 7. So there should be an array. 1, 2, 3, 4, 5. There's actually 8 there. So I will measure that. But that should be 1Ks. Should I measure them both, sod it, just so that I don't make a stupid mistake? Come on, boy. Right, okay. Ohmage. Stick that there. Okay, thanks for that, Moritz. Moritz is in the chat, everybody, which is nice. He's the guy who put all this together for Erica Synths. This is 1K. Look at that. Can you see that? Just about. There's a bit of reflection in that. There, that's a bit better. So there's often little bits that kind of are not always bang on as perhaps we thought they might be, but this is DIY. It's part of what that's about. And also part of my learning trajectory on this here journey is that components aren't always as important as you think. That you can have all sorts of different variations and that still be okay, and not to be quite so precious about it. So those are the 100Ks, those are the 1Ks, easy. Now it's these little squitty ones which are going to be the trouble. So this is an 18K. Yeah, there's one of those. So I'm going to have to write in terribly small writing. I might have to get me things on already. So this is, stay still, 1, 8. Might have to do a lot of measuring. So 18 there. This one. 50K, 51K, this is 50.6, is that close enough? We're going to go with close enough for 51K. Five, 1. Got 2 here, these should be 10. Yep. 10. 675. K, 68K, didn't I have that already? I had an 18. So that's 68. 68. K. Four point seven, 4.7K or 4K. Oop, 4K7. 7K. What is that noise? Yeah, if you don't have a this is a 6 point, this is the 6.8. What did you say before? 6K8. That's for the in place of the 2K there's a 6K8. Okay, which is what this is. We will get to this at another point. How are we doing? Good. So yeah, if you don't have a meter, then do just look up the bands. That's the other way of doing it. My eyes are too terrible for that just at the moment. 47K. 47K. I did that on the other one, didn't I? That should be 4.7K. I am not in a comfortable position. I might need to swap something around. That's 200. That's 200. That's what that is. 200. No, that's rubbish anyway. 200. I'm just going to have to remeasure it when it comes to it. Okay, so put that to one side for the minute. Bear with me a second. I've just got to do a bit of rearranging of myself because I've got a nifty keys down here, which is really digging in, not enabling me to sit comfortably. Oh, sorry everybody. Oh, I can shift in there a little bit more now. That's a bit better. That's better. Right, Faux Boson, God bless you. God bless you. Thank you very much. That's very kind. Right, so altogether that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. We have all of the resistors. Next we have a bunch of capacitors. Now that's all that and that in there. Do we? So we have two little stubby ones. Okay. I have one film one. This is a bit of a worry. Oh no, here we go. Here we go. A lot of stuff. Where are my glasses? Over there. I'm going to need to be wearing these permanently, I think, the way things are going. So we have 47, two 47s, two electrolytics. Good. 2 of those. 1 microfarad J63 film. Should have 5 ceramics, which will be these little fellas here. 2, 3, 4, 5, and 1 of something else, although I seem to have 2. These 102s? Yeah, I've got a spare 102, but that's okay. Lots of diodes, yeah, we saw those. 15 of those, the 4148s, and there's usually a pair of Schocky ones there. Those ones, got those, good. Bunch of transistors. Oh, right, okay. 5 of things, of course, there should be. 1, 2, 3, 4, 5, and I've got a separate one. So one of them is different. One of them is different. Is it this one? It's a 548. That says 547. 3904. 3904. 3904. 3904. 3904. Okay, so I've got 5 of the 3904s. Transistors. I'll put there. And then I've got one which is different, which says in the manual a BC547. This is a BC548. Now I hope that just means it's one better as opposed to something completely different. Anybody know? Basically, tomato, tomato. Thank you, Moritz. Good, good to know. Good to know. Careful of my magnets in there. Right, good. Next, couple of regular pots. So we've got pots and sockets in here. I'm not going to get those out right now. We're going to assume that those are all right because they're not as if they're difficult to see. Bunch of switches. It should be 5 plus 1, which is a triple throw. So which one is different? The one I was just picking up. Okay. So there's that lot, which you can't see. This lot here. Littler ones, let's just go one like that. And this one, which has 3 positions. Good, 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 good. A few LEDs. 5 off, apparently. 1, 2, 3, 4, 5. Yep, good. Oh, knock that stuff over. A bunch of jacks. Yeah, good. Couple of chips. Got chips here with holders. 1 of each. 4107. Yeah. And a 74. Yeah, op amp. What's it? Yes, we know all about those now. Some trimmers. There's one. There, weenie. Okie dokie. I'm going to get something in there. Did they say 2? There's another one. Okay. 5K and a 2K. Wonder how you tell them apart. Printed on the bodies. Are they? On the sides? Oh yeah, 2K5. And okay. Well, I've got 2K5 on that one, so this one must be the 5K one. I'll make that assumption. It has 472 written on it. Don't know. Well, we'll worry about that a bit closer to the time. Sockets, yeah, good, good. Right. So now we get to powering our breadboards. Now with this one, it wants us to start with 2, although that's not quite shown. Now, if I remember from the last time we put this together, I confused everybody and myself because the printing on my breadboard is actually backwards compared to what's in the manual. I don't think that's anybody's fault. And I can either choose to have it this way round and have the numbers wrong, and have the plus and minus right, or this way around and have the numbers right and have the plus and minus upside down. I think personally what I've gone with is to have the numbers right, so that I can see on the breadboards on the manual, I can better place where things are supposed to be because they're following the numbers. And then, you know, because of the way we're wiring up the power anyway, the plus and minus doesn't really mean plus and minus anyway. So let me get my two batteries out. I hope these are still lasting the day. They haven't just been sitting in there heating themselves up, which is probably exactly what has been happening. Surprised the whole shed hasn't burnt down. What are we on over there? Overhead? Oh, can't quite see. Yeah, I think so. Is that me? Yep. Okay, good. Right, yep. So this is how it sets. So I imagine, well, no, we're just going to have to read to see how it guides us putting the two together. But let's start with 1. So it's going to be, oops, it's going to be like this. And like I say, my negative and positive are slightly backwards. But the way we wire it up, we take the positive, which is the plus 9 volts, stick that on that rail. The negative goes to that side on that one. On this one, positive goes to there, which is, see, that is positive in this instance, and the negative goes to there. So that means, what it should mean, I think, is we get ground on this top rail and ground on this top rail, and we get plus 9 here and minus 9 here. That's how it should be. But no, I've not got this right yet. Hang on. Wait a second. I did something else. What did I do? Before, this is not quite right. This is not right. Or is it? I thought we had a piece of, I thought we connected them together with a cable. Didn't we? So, because this is not quite right. The batteries themselves aren't connected. So this is not quite right. So what I need to do is take the negative out of here, tie it into there, tie it into the negative into the positive of that one, and then take that and put that over to the top. Isn't that how it goes? So I've now got this negative, which is minus 9. I think that's how it goes. Does that seem right? Yeah, no, I don't think it's anybody's fault on as far as the breadboard thing goes. But isn't that's right though, isn't it? So I've got, if I'm going from just south to north this way round, I'm not going to use that because that colour is annoying me now. I'm just getting confused. Oh. So I'm sorry this takes me time to get my head round. So the negative is going down here, that's minus 9. In the middle, the positive and that negative have to be together. So that was in a previous one on the same rail when I looked at this. And then you take that rail and you plug it in to the top one over there, and then the last one, which is the plus 9, goes into that one there. I think that's right. I think that's right. Anybody tell me that's right? Alright, moving on. Okay, so sequence of basics. Before we dive into the circuit design, let's make sure we understand what a step sequencer actually does. So we have two separate types of sequencers, CV and gate. Let's bring up the manual for you. Two types of sequencers, CV and gate. CV is control voltage. We know this bit. It controls some parameter on a synthesizer. An oscillator gives out notes, that kind of thing. CV sequencers are really like strings of discrete voltage levels, a bit like sheet music for a synthesizer. So consider this example here. We've got a 5-step CV sequence where the output voltage increases by 1 on each step. Yeah? CV sequencer will take the sequence of voltage and sends them out one after the other via a single output, as if it's telling us the individual values in succession. Serial communication. Our sequencer still needs to know how fast it should step through the sequence, and for that we need a clock. A clock signal is really just a square wave oscillation going on and off at a steady pace. Our sequencer will then proceed to the next step every time the clock signal goes from off to on, or low to high. So the frequency of our clock signal determines the speed of our output sequence. Yeah. After passing the last step, the sequencer would traditionally start over with the first value in the sequence, giving us an infinite 5-step loop. So that's CV sequencers. Gate sequencers, on the other hand, are a bit simpler. A gate is just a voltage going from low to high and back to low again. It's a digital signal, essentially. It's a bit like a switch. To program a gate sequencer, we simply tell it whether you want a gate on or not. It will then go through these instructions again, advancing one step at a time in sync with our clock. Every time it encounters a gate on, it will send out a voltage pulse, resulting in a gate sequence that looks something like this. Are we talking about something like this? Yeah, okay, something like this. So there's the clock, on, off, on, off, on, off, on, off, and so on. That's good. In a typical patch, you would use this to drive an envelope generator, which in turn would drive a VCA or a filter, allowing you to add rhythm and dynamics to your melodies. Ideally, you want a sequencer to be able to send both types of sequencers at once, so it's able to provide both a melody and a rhythm simultaneously. And even though that might sound complex, it's really easy to achieve. Yay! Right, so to do it, we're going to use an old favourite from the synth DIY scene, the CD 4017. Oh, that old chestnut. That's good. It's a simple decade counter chip. What? It counts in decades, which means that it's able to count from 1 to 10. All right, thank you. For this, it has 10 states of outputs and a clock input. It's interesting that it counts from 1 to 10 and not 0 to 9, as is often the case in things. But anyway, oh look, here's how it works. When we fire the chip up, the first count state output will be on, meaning that it sends out a high voltage level, while all the others will be off, meaning that they're sitting at ground level. This tells us that the current count is 1. Now, whenever the signal we apply to the clock input goes from low to high, the current active count state output will turn off, and the next one will turn on, right? Meaning that the count has increased by 1. So the chip is basically just turning on its count state outputs one by one in sync with the clock. Right. I can see that, and in the diagram here, you've got 1, 2, 3, 4, 5, which is how many steps we've got. They've all got a sync resistor going down to ground. And you've got a clock coming in, going through a diode with a bit of a variable resistor, which is going to change the speed of the clock. That sort of thing. That all looks like reasonable electronics to me. Okay, so for this to work, there's additional input we need to pay attention to though. It's called the clock inhibit pin. Fortunately, all we have to do is tie it to ground. Great! This is necessary because the chip will only listen for a clock signal if that pin is sitting at a low level voltage. If you give it a high voltage, it will tell the chip to ignore stuff. We don't want that. Unless you want to sort of have some kind of bypass. Speaking of the clock input, you might ask what the diode and resistor are doing there. Well, kinda. Didn't we say that the chip is simply expecting a signal that goes on and off in regular intervals? If that's true, why can't we just feed it square wave oscillations from an oscillator? Well, because oscillators usually send out a signal that is centered around a 0-volt line, meaning that it swings between a positive and a negative. Oh yes, okay, yeah, sine waves and that. Problem with this is that many chips don't really like to receive voltages levels that are outside the ones we supply them with. In our case, we're powering it with plus or minus, well, 9 volts, but 12 volts in a what? Hang on. We're powering our chip with plus 12 volts and 0 volts. Okay. So applying any voltage greater than 12 or lower than 0 to the chip's clock input will be a bad idea. Worst case, it could kill it. Right, thankfully we don't need to worry about voltages higher than 12 volts because that's the maximum level in a typical Eurorack system. So we only shield our chip from negative voltages. To do that, we need a bog standard diode. Diodes are basically like one-way streets. Yes. We've done diodes. That's good. If we set up the diode so the arrow is pointing towards our clock input, only positive voltages will be allowed to pass through. Negative voltages, on the other hand, will try to suck the current out of the chip and the diode will block them. Do you have to think about current moving forwards and backwards when we talk about positive and negative? Or we're trying to remember in our earlier builds, we talked about voltage being like water, like a fluid moving through something, and water pressure. All those sorts of metaphors are being used. And so a diode allows flow in one direction but not back in the other, and that's a positive and a negative thing. But why the additional 100k resistor? Well, because without it the diode is blocking the clock input pin. While the diode is blocking, the clock input pin would be floating, meaning there'd be no defined voltage applied to it. This is a problem because floating inputs are prone to picking up noise, okay, which would cause the chip to behave in weird ways. So we use a pull-down resistor, which is just a decently big resistor going to ground after the diode. Whenever the voltage coming from our clock signal is high, a small current is flowing through the diode and resistor to ground. This is why the resistor should be relatively big, because you don't want to waste a lot of current here. When the clock signal swings low, the diode will block. But because the resistor is connecting the clock input to ground, it will be pulled down to ground level. It's as if the resistor was setting a default voltage that gets overridden when the diode conducts. So with this setup, we effectively chop off any part of our clock signal that might dip below the naught line, which should keep the chip safe and happy. Okay, so the 100k is essentially ensuring that it goes to nothing. You could just connect it to ground, but then it would all just go steaming into nothing, and that would be a waste of current, I think is being suggested here. Whereas you stick in a chunky resistor and you just get a small flow, but it still results in a 0 volts, I think. To try all this on the breadboard, we need to make the chip's internal state visible somehow. For this, we'll use a bunch of LEDs. Oh, cool. Attached to the count state outputs through current limiting resistors. These are necessary because LEDs are super quick to burn out. Right. Might be asked why we set up only 5 LEDs when the chip has a total of 10. Well, there's nothing stopping us from using all 10, but we decided to build a sequence with 5 steps. Alright. I mean, I'm not going to start drilling holes in the front plate. Assuming you're willing to go along with this, oh, go on then. Let's set up the circuit on the breadboard. You'll notice that a couple of tie points are simply labelled with a number. This means you should make a connection with long flexible jumpers, 1 to 1, 2 to 2, 3 to 3, etc. Okay. Mind the LED's orientation, they're essentially diodes, yeah. Which means that they'll only let current flow in one direction. Identify them by looking at the legs. Longer leg is the anode, which is positive. The shorter leg is the cathode. And it also has a slice off it, which tells us where the cathode is, where the negative side is. So we're going to have to build this, which is mostly, okay, it's wires, it's mostly wires and LEDs. This is interesting. So we're going to set this thing up. Right, so let me unplug a couple of wires before we do that so I don't break anything. Put this here, bring this in a little bit, I think. Get a bit closer. Are you alright out there? It's gone very quiet. Oh, right. All enraptured by my conversation. So we need the 4017, which is this one. I'm going to give it a quick squish in my magic tool. Now, I haven't learnt quite yet how to power both the boards. I imagine it's going to be simple, but it doesn't appear to be part of what we're doing at the moment. At the moment, we seem to be doing it all on the top board. That's cool. We're just going to go with it. So this, as I say, it's helpful to have the numbers. This is going, so 35 would be 1. 35 is, or the bottom pin seems to go on 40. So this is going between the two, bottom pin on 40. That looks good. So I'm going to put that in there. That's our chip, and I've put it in upside down. No, I haven't put it in upside down. That's good. Right. So unfortunately, I only have really long cables. That's just the way of things. But we'll cope with it. You hopefully will have something better than this. So we need to set up a nice little array. So it's going to go from, it goes from the first one straight across onto 7. So let's do each one at a time. So this is our LED. Enraptured as heck, yeah, okay. There's the flat side, and that's the cathode. Flat side is on the diagram, which is great. So the flat side, it's negative, is going to where this is. So where do they reckon it's going to go? Just there. So the positive side goes behind it. That goes in like that. Then I need a bunch of 1Ks. Okay, these are the 1Ks. 1K is going across the void from the positive, like that. And then that says 1. So the numbers on the documentation are to refer to numbers over here. We'll do that in a minute. We'll just carry on with what we're doing to start with. So the next one is going to go on the end of that, again from the ground, which is the top end. Yeah, that's right. I think. Yes, because that's coming from there. That's the ground. Ground, yes, yes. Okay, so this goes directly across. Like that. We take another one of these. That's a flat long leg positive. Don't forget, is our song. Long leg positive. Bumble, bumble, bumble. That goes across there. Good, next one. Cathode there, long leg positive. Number 4, long leg positive. And then we're nearly up to the chip. Okay, so there's some other shenanigans that need to happen over here. So we have this pin needs to go to positive. The pin next to it. So this is the clock side of things, I think, isn't it? No, I don't know. We'll look at that again in a second. That goes there. There's 100k. 100k, one of these. Which is going along to this third pin at the top, and that goes to ground. And there's another cable which takes the fourth pin also to ground. Now in between, I've got that from that 100k leg, still on that third pin on that side. I'm not sure of the actual pin out numbers, I can never remember which way around it goes, so I'm just describing, I'm not saying this is that pin, I'm just saying on the right hand side of it, that third pin, yeah? Are you with me? Good, good. This goes over here onto 42, 1, 2, about there. Yep. Then we need a diode. I think just one of the little ones. Because the big ones are usually to do with the power supply, aren't they? So the diode needs to go this way around. That goes next to that. And goes down a couple. And then we need a socket. Which backs up onto there. Is that right? That's right. And then we have another cable which takes that ground leg to ground. Good. There's a cable down the bottom there which takes this last pin down to ground, which is that inside leg. Inside leg. Good, so that's all the basic connections. Now we need to connect the pins from the 4017 to the actual steps. So let's see if I can color code this. That'd be great, wouldn't it? So I take pin 1, or rather step clock count 1, there we go, count 1, which seems to be on pin 3 on this side, of course, because that makes the most sense, doesn't it? This goes all the way over to here. Nice. So let's get a green one for count 2 is on pin 2. Nice, like that. Pin 2. I can see chat movement. Drink, yeah, not a bad idea. Noodle soup, what? Pork scratchings. Okay, good-o. Lovely, just as long as you're still with me. 3 is pin 4. 4 is pin 7. And 5 is 7 on the other side. 1, 2, there. That, as far as I can see, is all that's asked of me. So if I was to power that up, would anything actually happen? Because we haven't got a clock. So this, so that's going to that. Where does this go again? Oh, this goes in there. And this goes in this second one. Yeah, look at that, we got a light. We get a light. Oh yes, we get a light. So that's great, that is. I'm really enjoying this one already. So you'll need something like an LFO or a clock source. If you have one, great, plug it in to the clock input and see what happens. So what's the clock input, do you think? Oh, is it this? Can't I just like fiddle with it and then it will work? I mean, if I put a cable in and like lick the end, can I force it to work? Yes, see, look, I'm my own clock. Oh, I broke it. There we go. I'm here all week. Oh, I've broken it now. Oh, rats. Oh, there it's back. Oh, it's gone straight to there. So yeah, I don't have a clock to hand, but it looks like we're going to build one. Yeah, so Neil asked a question about these long horizontal lines. So what Moritz has done is he's just numbered, put some numbered squares. If I bring that back up, so you can see the manual here. See, he's numbered these. So rather than having these on the picture, which is going to get a bit messy, just gone like 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. Yeah, see it? Good, good. Worth checking out, I think. So to test it, you need a what's it? Yeah, we don't have that. But since our sequencer should have an internal clock anyways, we could take a slight detour and set one up now. So that's great. So we can do that, and there it is. That's a very simple thing. So we need an op amp, a few resistors, a potentiometer, and a capacitor. Da, da, da. We'll set it up and pick up a square wave oscillation at the op amp's output. Confused about how this works? Oh, always. Well, let's analyse it step by step. Okay. For that, we'll first have to understand what an op amp does. Basic concept is that every op amp has 2 inputs and 1 output. Think of the inputs like voltage sensors. You can attach them at any point in your circuit. They will detect the voltage there without interfering. No current flows into the op amp's inputs. That's why they say their input impedance is very high, near infinite actually. So why are there 2? Key here is the op amp is essentially a differential amplifier. This means that they only amplify the difference between the 2 inputs, not each of them individually. Let's check out a quick example. We'll imagine that one sensor, called the non-inverting input, is reading 8 volts. The other sensor, called the inverting input, reads 5 volts. Then, as a first step, the op amp will subtract the inverting input's value from the non-inverting input's value, leaving us with a result of 3, because 8 minus 5, gotcha, is 3. This result then gets multiplied by a very large number. Great, called the op amp's gain. Finally, the op amp will try to push out a voltage that corresponds to that result. Well, not a very high number if it just kicks out 12 volts, but let me go. These things here, is it going to go to a new page if I click on it? No, it's same page, but that's okay, we can go back. These things here are totally brilliant. Are we still on the manual? Yes, we are. So these little circuit things, there's links in the manual to these things here, which essentially do a simulation of the circuit that you're doing, and these are brilliant. Absolutely brilliant. Worth spending some time in here just checking out what's going on. But it's just given us a couple of op amp examples over here, and you can change the numbers in here so that you can make it be whatever you want. It just gives us a few examples of how those are different. Over here is a thing we're going to get to in a minute, but those are super worth spending time with. Let's see if I can find myself back in the right page. What I should have done is open that in another tab, but never mind. So back here, down. Okay, the clock generator. Good, 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 good. So the op amp is limited by the voltages we supply it. If we give it minus 12 and plus 12, the highest it will be able to go is plus 12. Will it? I suppose. So in our, but if we, yeah, okay, so sorry, that's not, so 12 volts is not at the input and plus 12 at the other input, because then it would result in 0, but we're just saying that the maximum and minimum we can give it is -12 and +12. So even though the result of the multiplication could be huge, the op-amp will simply push out 12 volts and call it a day. I see. So it was actually giving a huge amplification. It's just we don't see that because the maximum it can give us is 12. Right. So far so simple, but our clock generator in relation to the two input voltages of the op-amp's output is quite complicated. Because we feed the output voltage back, into both inputs. To simplify things, we can isolate the two feedback paths for now. Okay, let's start with the lower one. Here, the two resistors between output, non-inverting input, and ground form a 50% voltage divider. It works like this. By taking two resistances, connecting them in series, tying one end to a voltage and the other to ground, we can pick up a fraction of that voltage where they meet. Can we now? The relation between them would determine what fraction we get. Since both resistors are of the same value here, the op-amp's output voltage will be slashed in half before it reaches the non-inverting input. So we know that the voltage at that input is always exactly half of what the output voltage is. Because it's the relationship. So we know that the voltage at that input is always exactly half what the output voltage is. Because of the loop back thing. Okay, so because it's looping back, it's sort of, you have to get into rounds of time travel over what happens first, but the output is then feeding the input at half what the output was. That feels like it's going to disappear into some kind of black hole. Right, with the top half, things are a bit more messy because instead of connecting output and input with the voltage divider, we use a combination of a variable resistance and a capacitor. The resistance is made up of a fixed 2K resistor and a 250, or in our case I think a 6K8, and a 250K potentiometer set up as a variable resistor. All we have to know is that if we set one up like shown here, it will work as a resistor whose value you can control by turning a knob. Yeah, okay, sure. The added 2K resistor is then setting a minimum resistance so that when the potentiometer is set to 0, there's still some resistance between the op-amp's output and the capacitor. This is important because the whole idea is that we want to slowly fill and drain that capacitor by having a restricted amount of current flow from the op-amp's output, because that's what makes the circuit oscillate. Here's how. Imagine that we've just set this circuit up and connected our power supply. You might then assume that the voltages at the inverting and non-inverting outputs and the op-amp's output must be 0 volts. In theory this is true, which means that nothing should happen really because no current is flowing on either path. In reality there will be subtle voltage differences though, because we're dealing with the analog components in a non-ideal world. Because the op-amp's gain is so strong, we can expect the output voltage to either crash down to -12 or jump up to +12 immediately. Let's assume it's the latter. Then the voltage divider on the lower feedback path will set the voltage at the non-inverting input to be 6 exactly. At the same time, we'll see a small current flow through the potentiometer and resistor on the upper feedback path and into the capacitor. As it fills up, the voltage at the inverting input rises slowly until it crosses the 6-volt line. Then, because the result of the op-amp's input subtraction is now negative, the output will crash down to -12. Putting the voltage at the non-inverting input down to -6 with it. Yeah, because it's half of it. At the inverting input, the voltage will slowly start dropping down from 6 as the charge inside the capacitor is pulled into the op-amp's output. As soon as it crosses the 6-volt line, everything resets. The output jumps back to 12, pushing the non-inverting input's voltage up to 6, and the capacitor is slowly filling again. Since this process will repeat indefinitely, we get a constant square wave oscillation at the output. Better yet, we can adjust the frequency of that oscillation by the knob. Of course. I think I understand. I think I understand the idea. Now, if we were to go back to this picture, maybe that will help us. I'm just trying to wrap my head around. So what it's saying is, if in a perfect world, if you started it up, you'd have plus 12 and minus 12. So everything would just be 0. But because that doesn't happen, there's always a kick in one direction or another. So it's the top one. Take away that one. So when it gets to 6, it then drops. So this is going from plus 6 to minus 6. So this bit at the top here is causing this kind of triangle wave oscillation. We can adjust that. Here's bloody clever. So this op amp is essentially allowing for us to generate this square wave because we're filling up a capacitor, which then gets to a point that it flips over. I don't quite fully understand why it flips. Because when this is 6 volt, is it because I don't know. I mean, I'm looking at it and I appreciate what it does. I confess I don't really understand why. But I have just read through it all, so hopefully all you out there, you're not seeing it? Why aren't you seeing it? Oh, you're not seeing it. Yeah, okay. You're not seeing it. So that's because I'm in the wrong tab now. All right, so if I do it on the thing, on this one here, are you now seeing it? Yeah, okay. Thanks for pointing that out. Sorry, because I'm only capturing the tab, not the entire screen. So, yeah, as I was saying, this thing here, I can see what it's doing. I don't fully understand it. I understand that the capacitor is charging up and then it's discharging, and that's creating this triangle. And it's the maths somehow to do with this, which turns it on and off, which gives you a square wave over here. So it's this flipping here between plus 6 and minus 6 that is causing the square wave output. But I don't really know why it flips. Because when it's... But that's the idea. And you can slow it down and you can speed it up in order to give you your clock. But let's build it on the breadboard, because I don't want to get bogged down in something which, you know, is understandable, but I'm not quite, don't have the head for it just at the second. Right, let's re-find where we were. Oh, that's too far. See, there's a lot to do, and we're an hour in already, so let's get going. So this is the clock bit. Okay, so we got to here. So let's set this up on our breadboard and see how we fare. want to make sure that it's set up exactly as shown. If you reverse the power connections, it will heat up and die. Okay, now one thing that you haven't talked about here, Moritz, is how you power everything. You're not, because in the diagram about powering the board, you only had one board. So what do I do in the case of two boards? Now my assumption is that I just mirror it across with cables, yeah? Is it any more clever than that? So what I mean is, take that out of there for a second. So in the manual, you showed us how to plug the power into one board. So to plug it into two boards is my question. The intro says exactly that, yeah. Just jumper over. Just copy paste the rails. So I take this one here and put it into there. Yeah. This one, put it into there. This top one, put it into there. And this one into there. That simple. I mean, I appreciate that current always flows from left to right. No, I'm joking. All right, okay, good. So it was that simple. So let's just decouple for a minute, so that I don't blow anything up. Right, so I've got to get this other chip in. Sure it's the right way round, that way round. So this has got to go onto pin 50. That way round. 1 past 45, 1 past 45, pin 50. Yep. Okay, that's in. Right, I'm going to need a bunch more cables. So we seem to be taking our socket out. That diode is gone. That's gone. And then we take that from, that resistor is gone also. That's not right, is it? Or is it? Okay, so our 100k resistor, which was sitting in here doing something or other, that seems to come out, leaving a gap, mysterious, suspicious gap. And this is no longer going to that 100k, it's now coming across here from that third pin, still coming to here, and then being carried across the gulf to there, and that goes across to here, and then we have this 1, 2, 3 coming into the new board at 42. There we go, that's nice. Okay, then we have pin 4, 1, 1, 2, 3, 4. Going to positive. Then pin 51 going to ground. That's not quite going to the op amp. Getting another thing crossing the divide at the back here. What's that? Oh, it's a pot. Right. I've got something from this long one here, also going across. Now I've got all the mess going on down here, so I need my 100k resistor, which is this. That's not terribly clear. Okay, on here, I can't really, I'm not sure where the 100k connects to. I'm not sure what this is. Not sure what this black mass is here. Is that just a cable that's connecting pin 1 to pin 2 here? And the 100k, is that connecting to pin 2, pin 3? I don't really know. I mean, this is the diode, which is going to 3 and 1 past itself. 2, 3, that way around. So are you saying that the 100k goes from that 5th pin all the way to the start of the diode, the back end of the diode? That's not helping me. The 100k goes from chip, so yeah, to behind the diode then. So this here, as I'm understanding it, it's going from this pin 5 all the way across to here where it's connecting up with the back of that diode, and in between those pins 1 and 2 are connected together. So from pin 5 to there, and then in between pins 1 and 2 get connected together. Okay. I've then got a a 1 micro. Are they the 104s, a 1 micro capacitor, which goes to the back to this cable and that one pin in from the end. I then need a cable to go also from the back of the diode to the last leg. And from the inside of that leg to 55. So I've got me 200Ks, which is my divider. So I think what I'd like to do, I don't think we have time, but I'd like to look at the pinouts of the op amp so that I fully appreciate what I'm connecting things to. Because at the moment I'm just following the instructions, and that's okay, but I'd like to go, right, I need to go to pin 3 in order to connect the voltage divider, because that then takes the front of the thing back round to the other side. Do you see what I mean? And I could look that up, but I don't think we're going to have time to do that. But that would be something I would recommend if you are following this along. So this goes to ground from the end of that diode, and this goes to ground from the other 100K. It's messy. Oh goodness me. And then this goes to negative. Let's use a black in that case. This middle one goes to negative. Then I need a pot. I don't actually know which pot. I've got a choice between something that isn't labelled. B104, B254, B104, B104. So I'm going to use the B254 one because that's the different one, because we're talking about the rate, we're not talking about the CV levels, which is what the other 5 are going to be. So I'm going to take this one, which is called the B254, and I'm going to jam this in here. And this cable goes onto the outside leg. I'll push that in there. That should fit. I need the 2 legs wired together. And I need a 2K, which I don't believe I have. So it was the, it's a 4-7. That's a really messy something or other. That's an 18. Was it 6K8? I think you said it was a 6K8, yeah? Let's go back up to the top. So that's the one. There's a 68K. This is a 6K8. and this goes off pin 1. I kind of think there's something missing there. What's that going to? Is that all on pin 1? Shouldn't be, should it? That's missed it. No, but those two are. Yeah, and that doesn't go to that pin. It goes to the next pin. Right, pin 2. Got it. And this comes up to the edge of that. Okay. Yeah, it's a little complicated. I think I've got everything else in, haven't I? Over here, brought those in. The only cable that's going across is that one, which is presumably taking the clock to that clock input that was on the 100k before. This is now coming over there. Right. Since we've hooked our clock generator up to the clock input, you should now be able to see all LEDs go dark for an extended period of time as the count increases, state increases past 5. Okay, so what you're saying is plug it in and see what happens. Good, right, let's do that. So positive goes in there. I already get my light on. That's a worry. This one goes in there. Okay, I feel I might have done something now. I had a light. I did have a light. Did I blow it? Did I blow it? I don't know. Oh, there we go. Something. There we go. Got a slightly dodgy something going on. Woo! That's impressive. So my assumption is if I can grab this knob, I can turn it up and down, and it does fuck all. Right, okay, so it's very pretty. I'm not entirely sure what it is that's causing the pain at the minute. Oh, look, there it goes again. Right. Oh, there it goes again. Right, so something in here is not quite right. I mean, it's close to being right. I don't know. It's probably probably shorting something. That's to there. Maybe my capacitor's too small. Maybe it should have been the other capacitor. Okay, that leg isn't attached to anything. So what have I missed out there? That this one here is on the wrong leg, I think. No, actually there's a missing thing. That's what it is. Okay, so I've got a missing what's it. Let's take that power out of there for the minute. I've got a little cable which needs to bring this one here into pin 1. So there was some element not quite working. So pin 1 is hard to get to. It seems to be on the end of this one. Is that right? No, that's pin 1 and 2, isn't it? Can't fucking see. Okay. That, I think, goes there. If I can get that in. 2, 3. Okay, we'll try it again. Try it again, sports fans. Okay, nice blank lights. Or they might just be going really fast. Look at that. That's a bit more like it. Good. I think I used the 1 nano. That's the wrong capacitor. Could be, but I mean, I'm getting a thing, aren't I? I'm getting a thing. I mean, should it be... So not one of the 5 capacitors then? It should be the single capacitor, because this is the clock, not anything to do with the sequence. So what I should be using is one of these. Is that, I think, what you're saying? Let's see what happens when I do that. Let's take that out for a minute. It's like a game of operation. Here goes the funny barn. Right, so this goes in that space between dreams and reality. Alright, so I put that one in. Now you brook it. That's brooking it now, that has. That's a shame. Either that was now going too slow. No. Or I put it in the wrong place. No, I'm not getting anything now. Oh, I could put that in the wrong hole, that's why. There we go. There we go. See, I think it was better with my capacitor. Or I burnt something nasty. Yeah. Okay, so that's not happening. Let's put the other one back in. Hopefully not plug this in the wrong hole this time. Yeah, you see, I think mine's better than yours. It's the film cap. Oh, is it? Okay, right, okay. Alright, got you. I got you. There is a little bit of a disconnect between the breadboarding and the bill of materials, in that, you know, so this is a classic example, the one microfarad. I mean, I should have gone back and looked at it and known it would have been this one, I suppose. But yeah, a little bit of help would be no bad thing. It's like knowing which pot to use. I had to kind of make that up, or make a relatively intelligent guess, I suppose. But all of this is you know, a matter of intelligent guessing. So I need to get, how am I going to get that in there? I don't know. Is that going to fit? Right, well, I don't know. That's in as far as it can go. Great big fat thing. Is that? Well, I mean... Right, okay. Let's plug that in and see what happens. Right, so that's a bit more like a sequence. Yeah, it is all part of the fun. So yeah, great, that's awesome. So what we got now is it's obviously the counting chippy thing is counting through all 10, and we've got it counting through the first 5 in a good like this is a sequence kind of way. Excellent. I really like that. I mean, you've got to love lights, haven't you? I mean, anything that's going to turn a load of lights on, it's going to be a good fun thing. Right. Good. So we wanted to loop back. How do we achieve it with our thing? Well, resetting the loop. Good Lord. So using the chip's reset functionality, it works like this. Whenever we apply a high level voltage to the reset pin, the chip will clear its internal count state. Right. Setting the count to 1 and making the first step. So the reset is pin 2 over here, which currently is set to go to that ground. So we need to stick something in there. And that's going to come from 6. Oh, I see. Simply connect step 6 to the reset pin. Well, that's just bloody genius, that is. So, pin 6, no, not pin 6, number 6, which is pin 1 over here. That goes into, can't see very well. Into pin 2. So I need to take out the ground, don't I? Yes. So take out the bit that goes to ground. Look, I'm doing this on the fly. That's probably a bad idea. And this goes into pin 2. Look at that. Look at that. That's our 5-step sequence. That's glorious, that is. Loved it. Love it. Good, that's a whole page we got through. So it now should be trapped in its loop. And we could go ahead with 4 steps, 3 steps, and 2 steps. Yes, you can do that by just changing the number that it starts at. I get that. So we can do this with a module using a switch. So our 3-way switch that we spoke about, which is this one here. It's the equivalent of keeping our jumper plugged in one spot while moving the other end between fixed points. Yeah, totally get that. I think we all get that. Do we all get that? I think we get that. What are we looking at the moment? 4. Is that the overhead? Good. Yeah, okay, I was flying a little bit close to the sun there. So good. So the reset input. So in some situations it might be useful to be able to reset our sequence. I don't see why. Use an external trigger. For that you might be tempted simply to set up a jack socket and connect it to the chip's reset pin. Fortunately it's not quite that easy. Okay. Since the reset pin is always tied to one of our step outputs, there will be a straight connection between the step output and the new reset input. This is a problem because, for one, the path between reset and input and step output doesn't have any resistance. It's basically a short circuit, so if our reset signal is able to provide a lot of current, we might see our chip go up in smoke. Oh. Also, since the step outputs are connected to our status LEDs, we'll see them flash every time we trigger the reset input externally. Second problem is arguably more a subjective thing. It relates to the way that pin works. As long as there's a high level voltage present at the reset pin, the chip stops counting, meaning that it doesn't advance past the first step, essentially waiting for the reset pin to fall back to ground. So if you use a standard square wave signal to trigger a reset, the sequence would halt for a significant stretch of time, because a square wave has a high phase. So how do we pull this off then? Well, we use a basic passive gate to trigger converter. Nice. Which is really just a capacitor and a resistor. Set up like this. Reset, capacitor, resistor. Okay, first a positive one. When the input transitions from low to high, then a negative one which drops from high to low. Since we're not interested in the negative spike, it could potentially harm our chip, we eliminate it by using another diode. And a pull down resistor combination. This way only the positive spike will get through and trigger our chip. Same idea we used for the clock earlier. maybe. Well, let's have a look at them in the simulator, shall we? Okay. Okay. I mean, I thought capacitor was supposed to fill up slowly, which would give you like a ramp. I thought you would use that on a square wave to smooth it out into a triangle wave. So why is it suddenly going from a square wave to a spike? And why haven't I grasped this before if we've done this already? I don't know. Maybe I'm just not getting things quite so easily today. Anyway. The 100k pull down resistor ensures there's always a defined voltage at the reset pin. Okay, no matter what happens at the reset input and step outputs. Speaking of the step outputs, to address the first problem, to protect them from coming in through the reset input, simply use another diode we'll put between them and the reset pin. What? What? So, sorry, we're looking at the manual now. I need to put this on here. The cap is really small, so there's no resistance before it, so it fills up instantly. Okay. Oh. Okay, so right with this, my brain is melting. What page are we on? 19 out of 65. Gee, flippin' whiz. Okay. So a square wave. So a square wave goes square. Where we are. Square wave goes in here, fills this up instantly. But why then does it just get a spike out? Why doesn't it go? I don't. Why? Why does that cause a spike and not? Because it fills up and then can't get any fuller. So there's no more comes through, so you only get the front edge of that square wave. Is that how that works? Oh, brain. But then if we stick in a diode that way round, you're not going to get anything going on, are you? Because it can't go, it will go this way. Oh, no, I can't. Oh, I'll go back. No, I can't. So how is any of this happening over here? Aren't I better off just moving my cable? Can I manually move my cable and just stop it with all this switch nonsense? Simply use another diode. Cool, it says. Unfortunately, our two breadboards get crowded yet. So I've decided to omit the reset input from the suggested layout. If you want, you can set it up this way and test it out. No, that's fine. We're going to go with it. I understand the nature of the switching between the three things. Your circuit is a bit confusing me. but that's okay because I'm still a beginner with circuits, and so I will get confused at times. But I'm trusting that this all makes some kind of sense to somebody. Look, we've got a magic R number in the middle. What's that? Don't know. It's not really mentioned. All right, losing my mind. Okay, let's move on to the next page then. CV output. Now, this is more important because with this, we're going to be flipping, controlling things. Although, I mean, I have to say that as it is, the 5 lights is almost enough. This is almost enough at this point for me to go, yeah, it's a sequence. I get it. That's awesome. I'm getting a signal out. But we need to be able to set a control voltage for each of those stages. Now that, I don't know. We're about to find out how the heck we do that. Moritz says, imagine the cap like the head of a drum. You punch against it and you get a short thud. Okay. All right. So as cool as watching our lot, it is cool watching the LEDs. Where we're back onto the manual 5, yes. It's not sending out a sequence, so let's change that. So our individual steps are either sending 0 volts when they're off or 12 volts when they're on. And while we can't do much with 0 volts, we can do a lot with 12, because if we take those 12 volts and route them through a potentiometer and set it up as a variable voltage divider, we can scale them down to any voltage we like. That's awesome. Possible. Since conveniently a potentiometer is really just a voltage divider shoved into a single component, which allows us to change the resistance relation by turning a knob. Yes, yeah, I know, we get that. So let's say we add in a variable voltage divider after every one of the 5 steps. Then by turning the pots, we can set the specific output. Cool! We've got 5. Only problem is now we've got 5 individual outputs, 1 for each step. That's not really what we're looking for. We want a single output that gives us each in succession. Yes, that's right. Now, you might be tempted to simply connect all these together. Yes, absolutely. We'll just get the wires and we'll just spin them together. After all, the chip steps only send out 1 voltage at a time, right? Yeah, and those 2 steps are active simultaneously. That could work. Apparently, it ignores the fact that these 5 outputs can't just source current. They can also sync it. Oh, strange, funny words again. Which means that when one output is active, one of the outputs is active, current from that output would flow back into the other 4. This is not only shoddy engineering, it also means that the output voltage is much lower than expected. Okay, so you're saying that if they were just all connected together, the old water would be flowing up all sorts of different pipes. So we have to use a bunch of diodes again. Great. Diodes only let current pass through one way. Yes. Oh, look, we've got a thing to look at. Let's go look at it. Shoddy single output. So we've got our variable divider. Adjust me via sidebar. So you've got 12 volts. That's zooming along. Pot 1, this one? Yeah, okay. So we move that along there, and that changes the volts that are coming out of it. Yeah, we get that. Cool. So if we were doing a shoddy single output, got our 12 volts there, 0 volts, 0 volts, but we're losing some of it down this line here. That's the problem. And we're not getting a full amount out of here. Is this pot 2? Yeah. So we get, well, we almost get the 12, we just don't quite get it. We get down to the less of it. But you're losing stuff. Okay. Proper output with diodes and buffers. Alright, so we're using an op amp again to buffer it, because that reflects a thing with We did buffers before, so I'm going to totally assume that that's what's going on. All right, so if I change that, that changes the amount as well. Interesting. So which pot are we on now? Pot 4, pot 7, 6, 5. This one. Yeah, so basically put the diodes in the way, so then it stops the water flowing up the pipes. Yeah, easy. And then that creates a buffer. Yeah, got it. Good, right. Lovely. So now we're whacking down on page something or other down here. CV scaling, no, not quite. And we've got another, this thing here. Okay. So diodes, yes, did that. So here's our circuit diagram now with our diodes in place that we just looked at, and we've got a buffer there which keeps everything just buffering along nicely. No current flows back. Yes. This means that if the module we're driving our output, if the module we're driving with our output is even a bit power hungry, it'll make the output drop noticeably, and this is not ideal. Okay. One more additional thing, that's buffering. We want the output voltage to be the same in any and all situations. To ensure that, we use an op-amp based buffer. Buffers are great in situations like this because they allow us to make copies of the voltage without pulling any current. Yes, that's right. So by placing a buffer between our diodes and the output socket, we make sure the module we drive with it can pull plenty of current without the output voltage dropping. There's a whole current voltage business going on. Resistance, V equals IR. Oh my goodness. As a final touch, put in a 1K resistor, because we always like to put in resistors after the buffer's output. This is just to limit the maximum amount of current flowing into or out of the output in case of a short circuit. Right. Okie dokie. So, are we doing this? Look at this, boys and girls. Heck and all. This is all of the pots all the time. And we're going to need sockets, aren't we? Otherwise, how are we going to know? I don't know. Oh, because it goes to a single output. So where's our socket? Oh, right, over there. Right, okay. So look into this a little bit. So we have our single socket over there. We're going to probably need to plug that into something in order to see what's going on. Probably just use the scope, although I could easily enough plug that in. I plugged a cable in earlier. Yeah, okay, let's see, shall we? So let's take out me positives for the moment. So what's changed? That's all stayed the same. Okay. What I'm worried about on this particular breadboard, does it matter? Just to, yeah, indeed. Why not the VCO? Yes. All right, so on this breadboard, are we still on 5? Yes, we are. On the manual, the resistors. There's no connection between this LED and anything. Is that on purpose or is that by accident? Because there's not connected across the bridge here. I'm imagining they should be. Or should they be? Should those resistors still be there in the way? Yeah? Kinda. Okay. Okay. So I will leave the resistors in at the moment. Otherwise, as I say, the LEDs aren't connected. Right, okay, whatever. So, a few more cables then. I do have a whole other bunch of them. I don't want to get those into play. Couldn't I? I've still got a few more. Right. So pin 1. So these are just going straight across into the second bit. So pin 1, which is there, going straight across to pin 6. Yeah. Okay. We have another pin which goes to ground. Then we need a pot in between. 1, 2, 3. And we have another pin that goes across in the center. This goes over to the bottom on 5. Okay, so Moritz saying you want to drive the LEDs with transistors so we don't stress the 4017 too much. Okay. Alright. Poor old 4017. I am sorry. So 2 goes from there to there. It's a cable that goes from there to ground. Feels a bit crappy. Another pot. I've not got this right, have I? No, that should be 3. Should be the next one across. So that the middle pin is the one which goes across. Alright, this is all getting a bit silly. This needs to come back up here. It'll work. It'll work. I'm going to have to break into this pack of patch wires. So middle pin. Goes across. Alright, I think we might be there. Well, not there. I mean, we've done. I did a bit. Right, so I did all that, right? Did all of that. Right, good, right. Yes, good. So I've got me 5 things. Now we've got to somehow explore our way over to here to hit that. So that pot is still there. That's still there. My 100k is still there. That divider thing is still there. There's my resistor. This bit here. So what's new? I brought that cable across from there. Right, there's a diode. There'll be a couple of diodes. 4 diodes? Yeah, no, of course, there'll be lots of diodes. Anyway, so first off, there's a one which is heading towards the output. At some point it's got to use an op amp, hasn't it? Yeah, maybe. Oh, which is down here, not up there. Right, yes. So this is the op amp. So we've got to hook something in there to use that as the buffer. Cool, right. So somewhere we've got to take pin 3 out over there to 38. So pin 3, 1, 2, 3. 1, 2, 3. And there's 1 and 2 is also now connected up. Okay. 1, 2, 3 is there. That goes there, over to 38. 5, 6, 7, 8 there. Good. I've got those top 2 pins are now connected. This is our feedback loop in the op amp. See? I do remember. I do remember that other part of the op amp, which is pin 4, goes to positive. I've already got something in pin 4. That's already going to positive. That needs to be not there. It needs to be up there. That's better. Then that will make more sense. That cable's already going across, so that's good. And that's got to emerge, or rather, do that. Let's finish off my connections down here first before I get into that. Yeah, so I was dealing with a diode that way around, which comes off that a couple of bits, yeah. And there's a cable that crosses the divide off that one leg, which goes to there, simply across the other side. Good. Now I've got another diode. Now I've got lots of diodes. 4 if not. So that, okay, so that diode up there is actually for step number 5. That's what that diode is for. Okay. Because we're going a little bit flat here. Rather than got 4 of them across. So this one here I've actually done across should not be across. This should be coming over to this diode over here, because there's just not quite enough room. So this 5th fella here is going from that middle pin over to the leg on that diode. That front of that diode is coming over here, got another diode coming off that, going back a little way. Alright, there's like a row of diodes. This is hard to see. Okay, so from 37, 7, which is this one, does that connect to anything? There should be one back from the front of that. It is one back from the front. Okay, so 37. That goes back to 33, I think. 33, do we think? Really hard to see. I think so. Then there's another diode which goes on the same leg, one further up. And another diode does the same again. That comes up another leg. Got 3 diodes in a row. Oh, not quite on that one. And they all tag in together. Hope you're following this at home. Into there, into there. Oh my goodness me. I really liked having the LEDs flashing. And then this last one goes in there the right way around in the top above that cable on the same line, yeah, but then goes back kind of an unspecified number. Does it go one past that one? So therefore goes down to 32. I think that's right. I think that's right. Brain ache. Now I can connect these up to this first one here. This comes up to actually this top diode. This next cable from, I'm going to go up one from here, and this goes up to one further. So that's now going to that bottom diode. Complicated. This one, another one further up. This one goes to that other diode. And one more here, because that's all there's room for. That goes up to that top diode's leg, which is, yes, there. Freaky. Right, that's all that in. That's all that. That's got that in. That goes up to that leg. Good. That comes across. Got that little leg there. I've got a big one going over there. I need a. Is that off that one yet? Looks like I need another big one that goes here. No, that is that one. That's that one. So I need one to come off leg 1, which I don't have in yet. Gotta keep it track. So I'm there. That goes all the way across next to there. Then I need a 1K resistor. Is that these ones? Yeah. 1K resistor that goes 4. Yeah, 1K resistor. Then we patch socket. that goes to ground. That's already got a thing going across. Any other weirdness going on? I mean, right. Maybe I should order some small jumpers. Yeah. Right, okay, so okay. Come on, keep it together now. Don't lose focus. It's all looking marvellous. Now, I mean, I think I've done it. I think I have. So, I mean, if I plug it back in, is something bad going to happen to the LEDs? I mean, let's just check. I mean, there's, I mean, this, because there's still that, and this goes in here. So that's still working. No, it should be fine. Okay, good. So with that doing that, I'm going to bring this down and see if we can get some sound out. So if I just go back to here for a minute, my main camera. Envelope I did earlier, very exciting. So I need some sort of sound. I'm just crashing into things today. Oh, I've got a cable here that hopefully. Yeah, I think so. So what we should be able to do at this point is take a cable, plug it in here, plug it into the 1 volt box with a PCO, and we should get something happen. If we were to move the pots, look at that. Apparently, right, it's not great for dialing in individual notes. Apparently the precision, a little loud. This is because the CV range step is just too big. I mean, I thought it sounded awesome. But yeah, who's going to dial in anything on? Anyway, I made a bleeding sequencer. Right, so that's good. So great. So now they want to do some CV scaling. What sort of time are we on? Let's just see what else is next to come through. This button, I think. So we can scale it with a resistor and another sync resistor type thing. Which we could stick in. Yeah, so I'm just going to skip through status LEDs. Are LEDs back in? Okay, I'm already doing that. Okay, so it talks about pushing the 4017 to its absolute limits. So we're going to do something with the transistors. That's cool. Then there's a gate output, of course, we need. Oh wow, this is going to get, it's going to get manic on here. Fail-safe gate output. And then that's the end. Okay, I mean, if I think, because otherwise this is gonna go. This is quite a long build. I have a resistor leg stuck in my foot, as I always do. What I think we might attempt to do at this point is see whether I can just put the gate in. If I could put the gate in, I think that would be a good place to stop. Otherwise, we're just going to be here too long, I think. There's my concern. What about putting the transistors in, though? It's just going to be, is it going to be too much patching? I don't really know that I can see. The regular gate output should work fine. I think that's a good, I'm going to make an executive decision at this point that it would be good just to get the gate output, and then we've got the sequence thing going on. We've got the steps from the clock into the counter. We've got the voltage dividers, which give us the individual voltage amount, which then come out via the diodes of the output to give us our different notes. That's really good. If we could squeeze the gate in, we've got the clock obviously going in, if we could squeeze the gate and have that come out, I think that'd be a good place to stop. Good, yeah, I think that would be good. So we'll ignore the LEDs for the moment. The point being that Moritz was making was that the amount of current that is required to drive all of these is really taking the 4017 to its limits, and to make it safer and more reliable, he uses transistors instead to do something, you know, that whole business with currents and that. My volume is low. I'm probably just a little bit further away. You'll just have to lean in a little bit. I'll move this out of the way in a minute and then you'll be able to hear me better, I'm sure. So, status LEDs, that's okay, not do that. Gate output is what we're going to shoot to. Just try to get this bit done so we've got a working sequencer. And I think that will be enough. And then tomorrow we'll think of it again as we build the thing, solder the thing together. Hopefully these things will present themselves and we'll understand a bit more. Okay, good. So what we're looking at the moment, we're looking at that. Let me move this out of the way. We'll bring this back in a second when we know what we're doing. So, no, not going to go to that bit quite yet. Back to the manual. So, a gate is just a voltage going from low to high and back again. You might assume that our chip is already providing gates for us. After all, it simply turns its outputs on and off. Excuse me. So, we're essentially getting a gate per step, right? And if that were true, we could apply what we've learned from the CV output and set up something like this. Yeah, I mean, that makes sense, doesn't it? Each step gets routed through its own switch, followed by a diode. Then we'd simply connect them together and buffer the resultant voltage with another op-amp. Turning these switches on and off, we'd be able to decide if we want to have a gate on for a specific step or not. To make sure our buffer's input isn't left floating when a step's gate is turned off, we also need to add a 100k pull-down resistor. 100k pull-down resistor, so that when everything's off, it's not just floating. Yeah. Unfortunately, if we try something like this, you'd get something odd. With all steps turned on, the envelope won't get triggered. With the sequence of running, take a closer look at our step indicator LEDs. You can see one of them is lit at all times. There's never a moment when they all go dark. Since we are combining all the steps together, the gate output will be stuck at a high level permanently. Yeah. Simply because if one of the steps is high, the gate output will be high as well. So it will just be, yeah, okay. So because a gate, as we said in the beginning, is a voltage going from low to high and back again, how do we convert our output signal into a proper sequence of gates? This is where it gets tricky. We don't want trickiness. We basically have to make sure that our output always goes low before we reach the next step. Yes, so the gate length. Okay, good. Thankfully, we've got something to help us out with this. That something is the clock signal. Because if we overlay our current output and that clock signal, we see something interesting. Where the output stays high during each entire step, the clock actually goes low for the second half. Oh, yeah. Oh. So if we were somehow able to pull the output low whenever the clock is low, our problem would be solved. Yay! That's good, like that. All right, so we're back to our diagram here. So we bring the clock in. So we need an op-amp, obviously, because we always need an op-amp. 100k resistor and a diode. So we're talking about this this op-amp, 100k, 100k, and a diode. Right. Whenever the clock input is low, the clock's buffer output will also be low. Right. This will allow for current to flow through the diode and into the clock buffer. Now, without the 100k resistor in the center, this would basically result in a short circuit and burning chips. Okay. Because everything's flowing through here, straight to that. But this is slowing all of that down. But with it, we'd simply see the voltage at the gate's buffer input drop close to ground level as the clock buffer is comfortably eating up what's squeezed through the 100k. This is why we need the clock buffer, by the way, to ensure that we can sync all the current coming down through the diode. I still find it really hard to cope with voltage and current. I know I shouldn't at this stage. I should understand it. I mean I've got an O level from 40 years ago in electronics, where and a physics A level where I know that voltage equals current times resistance. you know, I've had that equation stuck in my head for as long as I can remember. But when we talk about, we'll see a voltage at the gate buffer's input drop. We'll see the voltage at the gate buffer's input drop close to ground level as the clock buffer is comfortably eating up what's squeezed through. I don't know. My brain is not working with this. You know, this is why we need a clock buffer, to ensure that we can sync all the current. Because we talked about that this will burn something out, but burns it out with voltage, burns it out with current. How is the current and voltage related? How is... I understand that the resistance resists the current. Because as you increase the resistance, the current gets smaller, because I equals V over R if the voltage remains the same. I don't know. I mean, that's true, but I think I'm just getting myself in a knot. Well, let's have a look at the simulator and see if that helps us. So the clock's going on and off. We already established that. And you've added in but in this diagram, couldn't you just take this whole bit out and you'd still get this output? Because this is turning on when this turns on, so it's just following the clock. Isn't it? Okay. All right. Sorry. I'm sorry if I'm having a bit of a brain fog at the moment. We just need to try to get through these gates to see whether we can work out how they go in. Gone too far. So it was all making some kind of sense, definitely, because all the clock's doing is trying to pull this back down again before it reaches the next cycle. That's all it's doing, and that's all we want it to do. So let's not get distracted into other things. So on the other hand, wherever the clock signal is high, the clock's buffer output will also be high. This means that the pull-down diode will now be pushed shut from below. Because of this, the current is blocked from flowing to the buffer, leaving whatever voltage we currently have at the gate's buffer state, the gate buffer's input, undisturbed. So no matter if the voltage is high or low, it will stay that way whenever the clock is high. Let's set this up on the breadboard and see how we fare. Yes, let's do that. Okay, let's give this a go, and then we'll call it a night. So here's our thing. Let's unplug our positives. So I'm ignoring the LED section at the moment. We're leaving that how it is. And we're just sort of kind of hoping we're not going to blow the whole thing up. And what we are trying to add in is, back up here again, is a bunch of diodes, one for each step, a couple of op amps, a few resistors, and the job's a good one. Right, to a single output ultimately. So where are we taking these from? So we're taking tricky to visualize. There's three diodes. Difficult to visualize on here. So I've got a diode at the top, and one in there. There's 5 diodes in total. This is really tricky. Right, we'll give it a go. Give it a go. I confess we are being hampered by the the volume of cables. Normally speaking, apparently, when you do this, you have lots of little ones. I didn't get lots of little ones in mine. Perhaps I have to make them. I'm not sure. I did have a look at one of these cables and thought, well, maybe it's this piece of wire all the way up, but it's not. So, I mean, I could just use a bunch of resistor legs or something. But having plastic coating is helpful because they wouldn't have any possibility of shorting. So maybe I just need to get onto Amazon or whatever and find some more, and that might make this less problematic. But as it is, here's a load more cables. Let's get them in there. Oh look, I've got different coloured ones over there. Let's bring those in. Let's go for orange and stuff. So maybe I should start with the diodes. So there's a diode, goes that way round. It goes on to the second from bottom leg. See, that's 5, that goes to 5, which is that cable there. So it's a 1 above it. And it goes directly 1 after. So that there to there. That to there. Vulcan modular has little ones, does it? Got that over here somewhere. I don't know. I don't see any little ones. They all look like big ones to me. I rebuke you and your little ones. Although they may well be little ones. I just don't know where they are anymore. That's not helping. Right. Okay, focus. Where was I? I was trying to go from here to there. Here's a cable. Let's go from here to there. So it goes from the end of that diode crying out loud. End of that diode. And this is one. Goes into there. Okay, that goes across. In 3 different places. those three in. Now, it looks like 0.4 has moved dramatically. So this, which was 4, has now been rerouted over there. It's interesting. So this is 0.4. That must mean that this has probably moved. No, it hasn't. It just goes over and 1. Okay, so that's 0.4 there. And that then feeds back to that leg. Alongside it. And then we use another diode. Just going to go that way round. It's just going to go from that 0.4 to there. That first one. That has gone into both. I don't know where it's gone, but it's not gone right. Come on. There. And there. Yeah, okay. That's in. And that's too far across. Let's go to that first one. Oh wow, this is too much. Mercy, mercy me. Got it. Right. Stop messing about. So that's there. Then got our 1K resistor, which is there. We should have 3 lines which go across. I've currently got these two which go from the 1K, yep, and that one which is the middle one. So there's another one which goes in between the two. Good. Okay, 3 more diodes. All facing the other way. Okay, one goes from, they all go to that same point. To 1, 2 and 3. And that same point is that one pin. I don't have the space. So what's going on here? So that cable needs to go in a little one. That cable's alright. This cable needs to go in one. room for 1, 2, possibly 3. Yeah, it wants there to be 3. Okay. So 1 to that one. 2, 3, 4. Yeah, that way round. Yeah. Right. That way round. Same leg here. One further leg there. Same leg, and leapfrogging to that one. 1, 2, 3, yeah. Good. That cable still remains. I've got my 3 in there. That still remains. Got something else going on over here. That goes across. Those are not anything to do with it. So I then take, or I borrow an output from here. Come on, that's on 51. So this is one less than 55. So that should go there. Over here, all the way over. One less than 55. Yeah. Something else in here. It needs to go from that last pin out to that. So that last pin, which has currently got nothing in it. That should have a 2 in it. Oh, because I'm using another op amp. That's what's going on here. So I need to short those 2 pins. Like that. Then take 1 pin out. It goes to this. Can I make that cable go further away? I can. Why don't I do that then? Okay, I'm going to move this to 52. Because it's just getting in the way. That goes to there. Now 100k has turned up from nowhere. To go, I did that already. No, to go across the top side. Got that one in. So I need 3, then to 1 out this other side. Come on, eyes. Put 1 out the other side. Oh no, there is room. Just 1 out the other side. To that 3rd pin. Yeah. Got 2 in between it. There's got to be another diode in there somewhere. Oh look, there's a 51k thing. I hadn't even spotted that. That looks serious. I'm starting to lose it. Okay, keep at it, keep at it. I've got a diode. Goes from that one to another 100k, which is going across the gap. Right, which is going to ground. So this is going to ground from the middle of here. That's ground, that's going to positive. So it goes next to that one. Next to it is pin 3. That's that 100k. That's that 100k. There's me thing. That way round. $68k. $51k. That doesn't say anything. Okay, so it might be that one. Looks like 47. That looks like 18. That looks like a 47 relation. That's a 10. That's a 1k, that's a 100k. So I've got that, which makes no sense. Oh, that's a 51. Right, yeah, 151. Gotcha. don't remember a 0.5k. So this goes one past the diode, same as the 68 leg. So 68 leg. One past the diode. Then it needs a mini one. And up after it. That should be, don't know what that should be doing. That takes another line up to ground. Ground being the top one. I think all I need is that 0.5. Is that what this one is? No, that's a 200. No, yeah, 200. 0.5k what then? 0.5k. Maybe one of my 4.7s is a... Did I get that right? That's 47k. Five, 4.7k. That's my 200. That's an 18. I don't know what this 0.5k is, I'm afraid. Sorry, Ken. Just going to go back to the beginning. Yeah, there's no 0.5k. I don't know what that's referring to. We have, don't have anything which is 0.5k. No, I don't have anything which is similar to that. Do I have something else? Is it a switch? Is it the switch? Is it referring to the switch? No, 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 that was something else. Is it the why would it be the trimmer? 5K trimmer. It's a trimmer. Right, well, it doesn't look like a trimmer. CV scaling, status LEDs, gate output. Is that what this is here? This 0.5K that looks every bit like that one. So it doesn't have any legs, so I assumed it just went across two things. That's a trimmer. Right. Okay, gotcha. Do you know if it's the black one or the blue one? I don't have any 0.5 anything. I've forgotten how to use those. So these have got 3 legs. So where does it go? They don't have 3 legs alongside each other. How does it fit? I don't understand. I think this is the last bit to put in, and it's really messing me about. Where does it, how does it go anywhere? And which one? I've got 2 and they're both 3-legged. There's no like, I don't know. Yeah, I guess what you're saying is that it's not 0.5K. That's the sign of a trimmer. And I don't have one of those boxy trimmers. I've only got these trimmers. Or do I? No, I don't think so. So it's going to have to be one of these. It's not very clear, I'm afraid. Am I going to have to squeeze this together in some way? Use a 4K7 resistor. Okay, but what's it plugged to? Because it seems to cover 3 plugs. It seems to cover, if I put the manual back on for you, which pins does it go between? Because I've got potentially 3 pins if it's the trimmer. Does it go to the 51K? Does it go to this side of this one? Does it go to this side of this one? Or doesn't it matter because that's essentially connecting the same thing to the same thing? So can I dispense with that small one and just connect the 4K7 from the 51 to this line here? You can omit the small jumper. Goes from 35 to 33. Okay. And which one does I need 4K7? Did I decide I know which one that is? I've got bloody 2 here that I don't really know. Door. 4.7, so that's the 4K7. In electronic speak. Right, back in again, back in again. So I can pull out this little one. And I can go there to there. Right, I've still got a plug. Still got a plug to put in at this end. But otherwise, it's getting close. It's getting close. So this goes up and over. I use a 1K. Flipping Nora. I think that might be it. I don't know. There's a. Oh, I did that. I did that there. Well, whether it is or it isn't, it's got to be worth a go at this point. Okay, trauma. Last chance. Let's see whether this pulls it together. Or if it still lights. I mean, that would be something, wouldn't it? Yeah, which it's not at the minute. So, oh, I've probably stuffed it up somewhere. That's a shame. That's a shame. That's in a minus. That goes there. That goes across. No, that's still the wrong place. There we go. Okay. I've got a weirdness going on there with those two. Okay, that's better. So, what I've got to do is plug it back into the to the rest of it to see whether I can get the gate to fire. Whew. Right, so let's put it back onto here. Come on, push through. We can do it. Come on, we can do it. Where's the power supply? Here. Oops. Keep that down nice and low if I can. Bit too low. No, oh, I've just broken it. I haven't turned it on. So what I'm going to do is take the out of the pulse wave into the VCA. Sorry, I'll speak a bit louder because I'm a bit further away. It's not going to be loud. It's going to feel a bit further away from my microphone. I will try to remember to speak up. So this is the CV output, I think, into my 1 volt per octave, and then I need my gate output from here, firing flipping envelope. Exactly. Then the output of that doing that. Yeah, okay. Now there was far too much room for me just to completely stuff it up with all of this. So I'm still getting show you the breadboard. So I'm still getting the notes. So that bit's working. Let me see if I can how can I do this best? It's tricky. It's tricky. Did I get a gate then? Try to put this to one side. A little bit. Then I can look at this a little bit more successfully. So it's the gate output, this output. Once you start wobbling stuff. So that stuff's all good round there. It's going to have to be something to do with a short in here. Or this crazy ass weirdness over here. Did I do enough on that? Did I put enough stuff to ground on that op amp? Like here, for instance. I don't know that I did. Why is this giving me so much bother tonight? So I've got that, which is, it's not even the top pin, is it? No, that's outside the top pin. So I should have 100k going across to ground. Yeah, I should next to it have something going across to positive, which I do. I should have a short there, which I do. The 100k travels across it and goes to the next one. Yeah, the 100k goes onto that middle line. Really hard to see. Yes, it does. Goes to that middle line. That one goes to that diode. Is that diode the right way around? Yes, it is. That comes all the way back to the 100k. Yeah. That goes across to there. Yeah, they all go across to there. Yeah. Took that pin out. That's now connected just to that resistor. That should be right. Is there anything else changing there? Those are all good. That one is going the opposite direction, yeah. Yeah, okay. Got me one. Oh, was that a thing? No, I'm just pulling out. Right, so there you go. Moritz, thanks very much for your contribution this evening. That was really useful. This was hard, man. This was a hard one. Difficult. Obviously, it's it's difficult because of my my long cables is definitely a factor. Without a doubt, it's definitely a factor. But there we are. So, yeah. So sadly, I wasn't able to get the gate to work. I don't know. I mean, I can keep going through the breadboard, but my brain has melted now. I don't think I can do any more. So I think, ladies and gentlemen, that's as far as I'm going to get this evening. I'm sorry it wasn't quite as successful as I would have liked. I mean, I really enjoyed getting the lights to work and then moving on to getting the notes to work. I mean, that was awesome. That was spectacular. I like that a lot. It's just got too much in here. It's just too much. And so I don't think I can take it any further at this point. So what we'll do tomorrow, I'm going to go and have a good night's sleep. We'll come back tomorrow. I might fiddle with it a little bit during the day. I might not. But tomorrow evening we'll get down and solder it. So I think that'll be a hefty thing to do on its own. And hopefully through the soldering we'll be able to see where the op amps go. We'll be able to see how the different things are addressed. And maybe we can clear up the whole gate business. Because, I mean, this is not because there's anything wrong, but it's because I haven't quite, you know, there's going to be something which is just not quite right. Not quite in the right place. And it's hard. It's really hard to see when you've got a forest of cables like this. So evidently I need to get some better cables, smaller cables. I mean, we kind of knew that from the start, but I was getting away with it. I mean, it may be because it's on batteries, says Ken. Okay. Possibly. I don't know. How would I don't know. I don't know about those sorts of concepts. Maybe my batteries are low. I don't know. Anyway, I don't know about these things. All I can do is what I've done in front of you. And at this point, we assume that I've crossed a wire or connected up something not quite to the right thing, or perhaps part of my breadboard's not completely functional. Don't know. But we learnt a lot about how the sequence is created, about the creation of the voltage, about the stepping of the steps, and potentially of the gating of the gates. But we just haven't been able to enable that to actually function. But I mean, all of this is a learning experience. It's all supposed to be a learning experience. I mean, and as I said about how I'm not really seeing the different op amps on the chip anymore. You know, there is a little bit when Moritz goes from the text to the breadboard. I would like there just to be a little bit more information over what some of these components are. I mean, this trimmer, this what I thought was 0.5K, which is a bit weird when you think about it. You know, it just needs to be. It needs to be pointed out, I think. Otherwise, if I sat here with none of this conversation that we're able to have, I'd have no idea what that was and would be completely stumped. I would have to, I don't know, reason it through or go back to the schematic and try and work it through that way, which is hard. So I don't know. It's tough. This is difficult stuff, and Moritz has done a fantastic job of trying to get this across into some kind of level where, you know, reasonably switched on people can understand, can grasp it, because this is proper electronics, and I think it's evident in how I'm working my way through this. There are gaps in my understanding. Absolutely, there are things I can't quite gel with in how. And when you're talking about, you know, we seem to talk about voltage and current interchangeably, and that drives me nuts because there's different things going on. There's not enough current to drive something, but I thought we were talking about voltage. Well, we are talking about voltage. Well, then what's current got to do with it? Well, because of the resistance, obviously. So what? So we're pulling current through things, but not backwards. But then you've got two diodes facing each other. What goes where? And how are you taking that? I don't know. Like I say, it's a little bit of knowledge is a dangerous thing to a person like me. So, well, I appreciate very much that you found it fascinating to watch. That's amazing, because sometimes this feels too hard, too hard. But I'm committed to doing it. I am solidly committing to working my way through it, and tomorrow we're going to solder the bugger together and get it running in our case, and that will be awesome, because it's a great little sequencer. I'm looking forward to having it running properly, and I love the fact that I got some lights to light. You know, I'm a simple person. Simple things. So cool. Yeah, Mr. Livestream, Mr. Live Review, this is nuts. You are right. You are right about that. You have to do the final step with the added transistor, says Moritz. Okay. Well, I think, as I say, I think we've gone far enough. So it may well be that this is working. It's just not quite generating enough voltage, and there needs to be a little bit of shimmy shammering going on inside there to make that happen. But, you know, I've skipped pages in order to get to just to do this bit. So who knows? Who knows? There's something about this fail-safe output. In order to boost the gate output to 12 volts. Well, maybe I'll come back and look at that tomorrow. Maybe I will. Just that little bit. That doesn't look too hard, does it? Oh my God! I don't know, it might do. Extra stuff going on over here. And I already used my 4K7. Awesome. So, I don't know. Maybe I'll look at that tomorrow. Maybe I won't. I'm not sure. I'm not sure at this point. I might have got over my interest in this one and wanted to move on to something else. Anyway, thank you ever so much for spending some time. 3 hours with me, fiddling around and faffing around with this thing. Oh, crikey, my head hurts. So yes, tomorrow. Meet you back here, same time. We'll solder the thing, see how we go. See if we have a slightly smoother thing. Use stream instead of electrons. Okay. That would be great. So yeah, back here tomorrow for soldering, and in the meantime, thanks very much and all that, and go make some tunes. And I will slowly fade away into something. What's the outro? That one. Yes, good. Great. All right. Thanks ever so much. Take care. See you tomorrow with a bit of luck back here. Take it easy.